picking up good vibrations.
Let us now have a look at some properties of systems. The first one is causality. A system is causal if the output at any time depends only on values of the input at the present time and on values of the input of times in the past and not on future values. In other words, if two inputs are identical up until a given time t, the output must also be identical at time t. The signals can differ for future values, but if they are identical up until the same time t, the outputs must also be identical. A few examples of causal systems. First difference. Y of n equals x of n minus x of n minus 1. It's a causal system, but a very related, very similar system, which is x of n plus 1 minus x of n, is non-causal. Why? Because at time n, the output would depend on the future. An example of a causal system in continuous time is x of t minus delta, where delta is positive, so a delayed system. And an example of an non-causal system is y of t equals x of t plus delta, where delta is again positive. So basically, a causal system is a system that does not depend on the future. Now, you might be wondering, well, what is then a non-causal system? Because we cannot make our systems depend on the future. For instance, if I'm processing my voice, I cannot make it dependent on what's going to happen in the next 10 seconds. However, if I record my voice and I post-process it, I can make that my voice right now and make a filter that depends on what's going to happen in the next 10 seconds. And that's because the independent variable in the first example is the time that is running right now for me. And in the second example is the time that has elapsed in the past. So we can be non-causal, there can be systems that are non-causal, it all depends on what we call time. Memory, another property. A system does not have memory, is memoryless, if the output at any time, t or n in discrete time, depends only on the values of the input at the present time, not on the past or future values. So basically, for instance, in discrete time, a memoryless system can be a multiplication by a scalar, because y of t equals 3x of n, y of n equals 3 times x of n. The value of the output at time n only depends on the value of the input at time n. A system with memory is the first difference, y of n equals x of n minus x of n minus 1, because this one depends on values of the system in the past. So whenever the output at time n depends on values of the system, either future values, say xn plus 1, xn plus 2, or past values xn minus 1, xn minus 2, etc., the system contains memory. In other words, I have to store, to compute the first difference, I have to store x of n minus 1 in my memory to be able to compute the output, which is x of n minus x of n minus 1. A system without memory in continuous time can be, for instance, the power, y of t equals x squared, and a system with memory can, for instance, be a delay, y of t equals x of t minus delta, because I have to store x of t minus delta to compute the output. Linearity. Let us say that we have a given signal x1 that we input to our system and we get y1. And we have x2 that we input to our system and we get y2. What happens if we input to our system x1 plus x2? For the system to be linear, we must obtain y1 plus y2. Besides that, if we input to our system a scalar times a signal x1, alpha times x1, we have to have at the output alpha times y1. A system is linear in short, if it satisfies the superposition property. And it basically says that if the input consists of a weighted sum of several signals, the output is a superposition, that is, the weighted sum of the responses to each of these signals. And the same holds true for an infinite sum. So let's say that if the input is an infinite weighted sum, the summation from I equals 0 until infinity of alpha I times xi of k, and each xi of k corresponds to an yi of k, then the output must be the summation from I equals 0 until infinity of alpha I times yi of k. Some examples of linear systems in discrete time are, for instance, a multiplication by a scalar is a linear system, and in continuous time, a delay. You can check that indeed these two systems are linear by checking the properties. For instance, if you multiply x of n in the first discrete time system by a scalar, let's say 5, the output will be 15 times x of n, which is nothing more than 5 times the previous output that you got when you only applied x of n. Examples of nonlinear systems in discrete time are, for instance, a multiplication between x of n and x of n minus 1 that gives us y of n. It's nonlinear because, for instance, if I apply alpha, or let's say 5 times x of n, I'll get 25 times x of n minus 1, which is not 5 times y of n for the original signal. Continuous time, for instance, the power is also an example of a nonlinear system. Last property, time invariance. A system is time invariant if we know that if we apply x, we get y. If we shift x and we apply x of t minus delta, we get y of t minus delta. A few examples of time-varying and time-varying systems. In discrete time, an example of a time-invariant system is a multiplication by a scalar, 3 times xn, and also delay. And in examples of time-varying systems in discrete time is if we multiply x of n by n, or in continuous time, if we add plus 3 times t to the signal, these systems will be time-varying.